Parametric hypothesis tests are based on the assumption that your data have been sampled from a normally distributed population. In practical terms, we can argue that this assumption has been met if our sample data are normally distributed. In SPSS, there are many ways to assess the normality of a set of scores. So here we're looking at a data set from Allen, Bennett and Heritage. Two experimental conditions are being compared on a continuous dependent variable, which is speed. So the objective of this video is to make a judgment about whether or not the scores in each condition are reasonably normally distributed. So in the Analyze menu, select Descriptive Statistics and then Explore. Move the variable that you're assessing into the dependent list, and if you have a grouping variable, which you will have for an independent samples t-test or ANOVA, move it into the factor list. Now if you don't have a grouping variable, which will be the case for correlation-based analyses like multiple regression and factor analysis, as well as repeated measures t-tests and ANOVAs, then you can leave the factor list empty. In the Plots dialog, select Histogram and Normality Plots with Tests in addition to the defaults. And now you can click Continue and click OK. Now this provides us with quite a lot of output to assess, and firstly I want you to note how we have a separate set of output for each of the conditions. So a separate set of output for each level of the variable which I entered into the factor list. Now the first part of the output that we can look at are the skewness and kurtosis figures. Skewness is a measure of symmetry, whereas kurtosis is a measure of how tall or flat the distribution is. When both are zero, the distribution is approximately normal. Now as a rough rule of thumb, if the skewness and kurtosis figures are more than twice their standard errors, then you have cause for concern. Now here they're not, and that's good news. Now the Shapiro-Wilk test tests the null hypothesis that the data was sampled from a normally distributed population. Obviously you don't want to have to reject this null hypothesis, so you want this test to be non-significant, and it is here for both conditions. Now a histogram should look reasonably bell-shaped, although with so few cases in each condition it's not always going to. What you can do though is overlay a normal distribution by double-clicking the graph and then selecting Show Distribution Curve in the Elements menu. Okay, so moving down, we have a histogram again for both of the two conditions, and underneath those we've got two stem and leaf plots. Now, a stem and leaf plot is essentially a histogram rotated 90 degrees clockwise. It gives a little more information than a histogram though, because it plots every score in the distribution. So here, for the first condition, we can see that there were two cases with scores of exactly 30, one with a score of 31, one with a score of 32, and so on. Now a normal quantile-quantile plot graphs the observed data against the values that we would expect if it were normally distributed. The diagonal line represents the normal distribution. If the sample data are normally distributed, then the points should cluster tightly around this line. A detrended normal QQ plot just graphs the deviations from the diagonal line in the normal QQ plot. And what we're looking for here is an even spread of points above and below the line. Finally, box plots give you another indicator of skewness. The black line is the median. The box represents the cases between the 75th and 25th percentiles, and the whiskers are the highest and lowest scores that are not outliers. If there are any outliers, they'll be marked as a circle or asterisk beyond the edges of the whiskers. So looking at all this evidence then, I think we can conclude that the two sets of scores are normal enough, although they're certainly not textbook examples of normality.
In the data file, we have several variables, one for each question on the questionnaire. If we look at the value labels, we can see that a 0 was entered if the participant said the statement was false, and a 1 if they said that the statement was true. If I change to the data view, I can see that the first participant rated all of the statements as false. To calculate the Kuta-Richardson 20 coefficient, we open up the Analyze menu, go to Scale and Reliability. We move all of the items into the Items field. We open up the Statistics menu and select Scale if item deleted. Click Continue to close the menu and OK to estimate the coefficient. In the data file, we have two variables of interest. We have the first therapist's rating of depression severity and then the second therapist's rating. We can see that depression is scored with 4 levels, ranging from no depression to severe depression. If I change the data view, we can see that both therapists rated the first individual as having no depression. To estimate the intra-class correlation for inter-rater reliability, we open up the Analyze menu, go to Scale and Reliability Analysis. We move both of the ratings into the Items field, and we open up the Statistics menu. Select Intra-class Correlation Coefficient, and in the drop-down, make sure that two-way mixed is selected, and in the type drop-down, that consistency is selected. Click Continue to close the menu, and OK to run the analysis. In the data file, we have two variables of interest: the therapist's first rating of depression severity and their second rating. We can see that depression is scored at 4 levels, ranging from no depression to severe depression. If I change to the data view, I can see that the therapist rated the first individual as having no depression at both sessions. To estimate the intra-class correlation for test-retest reliability, we open up the Analyze menu, go to Scale and Reliability Analysis. We move both of the ratings into the Items field, and then open up the Statistics menu. We select Intra-class Correlation Coefficient, and then from the drop-down box, we want to select the one-way random model. Click Continue to close the menu, and OK to calculate the coefficient.
Here we're looking at a researcher and a research assistant's independent ratings of the severity of 35 instances of playground bullying. If we toggle the value labels, we can see that 1 indicates mild bullying, 2 is moderate, and 3 is severe. And in most instances, the two researchers' ratings agree. However, that's not always the case. Now, weighted kappa isn't available in SPSS by default. However, we can add it as a menu item by downloading an SPSS extension, and you'll only need to do this once. So in the Extensions menu, select Extension Hub, and then search for kappa. So this is the extension that we want, weighted kappa. So tick Get Extension, and then OK. And there's a license that we need to agree to the terms of. And the extension is just installing. Excellent. So now when we go to the Analyze menu, in the Scale sub-menu, we've got a new menu item, Weighted Kappa. So we need to move the two sets of ratings into the Rating 1 and Rating 2 fields. And underneath there's the choice between linear and quadratic weightings, and in most instances linear will be appropriate. So if we click OK, now the output for weighted kappa is very simple. The kappa figure here is 0.869, and that represents a good level of agreement between the two raters. And if needed, there's also a confidence interval around kappa that you can report, and a significance test. And the significance test is simply testing whether our kappa departs significantly from 0. And here it does.
In the data file, we have two variables of interest, the ratings of the student and the ratings of the supervisor. We can see that these variables are nominal and that they can take on one of three values. 1 for a rating of secure, 2 for insecure avoidant, and 3 for insecure resistant. If I change the data view, we can see that both the student and the supervisor rated the first infant as having secure attachment. To estimate Cohen's kappa, we open up the Analyze menu, go to Descriptive Statistics, and cross tabs. We move one of the ratings into the rows field and the other into the columns field. Next, we open up the Statistics menu and select kappa. Click Continue to close the menu and OK to estimate Cohen's kappa. The first table to look at is the classification table for block 0. This is the block of the model with no predictors entered. Here we can see that the model can correctly predict 66.7% of cases simply by predicting that no individuals had left. The omnibus test of model coefficients in block 1 shows how the model changed when the predictor variables were added. We can see that the chi-square value is significant in the modelled row, which indicates that adding the predictor variables significantly improved the ability of the model to predict the employees that would leave. The model summary table underneath gives R-square equivalents for the logistic regression. Generally, both are reported. Next, we have the Hosmer and Leemshow test. This assesses whether our model is significantly different from a good fitting model. As the test is non-significant, our model would seem to fit the data well. Under this, we have the classification table for the model with the predictors added. We can see that the new model is 90% accurate, whereas the model without any predictors was only 66.7% accurate. Next, we look at the table for the variables in the equation. We want to look at the XB column for the significant predictors. This is what's known as the odds ratio, and it represents the change in the probability of our outcome variable occurring. In this case, the change in the probability of individuals leaving the workplace. A value of 1 means no change in probability. A value greater than 1 indicates that individuals are more likely to leave, while a value less than 1 indicates that individuals are less likely to leave. We can see that job satisfaction has an odds ratio of 0.076, which means that a 1 unit increase in job satisfaction is associated with a 92.4% decrease in the probability of individuals leaving the organisation. Below this, we have a plot of the observed groups and predicted probabilities. This is another means of assessing the fit or accuracy of our model. Here, we can see that as the predicted probability of individuals leaving increased, the number of individuals that were observed leaving also increased. This indicates that our model has good predictive accuracy. When reporting the results of binary logistic regression, you would generally report the omnibus test of model coefficients, both R-square statistics, the Hosmer and Leemshow test, and coefficients and confidence intervals from the variables in the equation table. First, we have the reliability statistics table. The coefficient is labelled as Cronbach's alpha, but because our scale consisted of only binary items, the coefficient is equivalent to the Kuder-Richardson 20. Here, we can see that the reliability was quite good, equal to 0.870. Below this, we have the item total statistics table. The main column that we are interested in is the alpha if item deleted column. This shows us how the reliability of the whole scale would change if an item was removed. We can use these values to assess if there is a particular item that is heavily impacting the overall reliability of the scale. However, we can see that none of the estimates are greatly different to the overall reliability of 0.870, and as such, this indicates that none of the items should be removed from the scale. Our main table of interest here is the intra-class correlation coefficient table. And here we want to look at the single measures row. Here we can see that the coefficient is 0.745, which is relatively low. We would then look at the confidence intervals for the estimate and see that they are quite wide, ranging from 0.61 to 0.84. Overall, this would indicate a relatively low level of inter-rater reliability. The final result to look at is the F-test with true value 0 column. This tests whether the intra-class correlation coefficient is significantly different from 0, and here we can see that it is. However, as these data show, just because the coefficient is significantly different from 0 doesn't necessarily mean that the two raters have high reliability. Our main table of interest here is the intra-class correlation coefficient table. Here we want to read the results from the single measures row. We can see that the coefficient is 0.737, which is relatively low. Then we would look at the confidence intervals for this estimate, which range from 0.599 to 0.832. Now these are quite wide, which overall would indicate a relatively low level of test-retest reliability. The final result to look at is the F-test with true value 0 column. This tests whether the intra-class correlation coefficient is significantly different from 0, and here we can see that it is. However, as these data show, just because the coefficient is significantly different from 0 doesn't mean that the ratings have a high level of reliability. First, we have the cross-tabulation table. This is simply a summary of the students' and the supervisor's ratings, and allows us to see the classifications that the two agreed on and that the two disagreed on. In the symmetric measures table underneath this, we have our estimate of Cohen's kappa, which we can see is 0.798 for this data, which we would consider as being very good. We would denote kappa with a lowercase italicized Greek letter kappa.
When you run the Crumbach's alpha procedure in SPSS, you get several tables of output. The first tells us that these analyses are based on 62 cases and that there were no missing data. The second table, called reliability statistics, contains Crumbach's alpha, and in this case it's 0.888. Now, different authors give different recommendations, but general consensus seems to be that anything over about 0.7 indicates that the measure is suitable for research purposes, and anything over about 0.9 to 0.95 suggests redundancy. So in other words, several items asking basically exactly the same thing. Now, before reporting this figure though, it's always a good idea to scroll down to the item total statistics table and check in particular the final two columns. Now, the corrected item total correlation column tells you the correlation between each item and the sum of the remaining items. A particularly low item total correlation for an item indicates that it's not strongly related to the others and may need to be removed from the scale. The final column is Crumbach's alpha if item deleted, and it reports exactly that. It's Crumbach's alpha calculated on the other 9 items. So alpha if item deleted is 0.873 for item 1. This is what alpha would be if it were calculated only on items 2 through 10. So when looking at this column, you're scanning for any values that are substantially higher than Cronbach's alpha for the full measure. In this case, removing an item wouldn't improve alpha, which is already 0.888. It wouldn't improve it substantially. Now, if you do decide to remove any items from a scale like this, don't do it purely based on the results of a reliability analysis. Always consider the information that you have here in the context of both validity. So will the measure still be measuring what you intend it to measure if some items have been removed, and also factor structure. And for information on running factor analyses, you can refer to either the StatHand app or the website. We are looking here at a correlation matrix. The matrix is mirrored on the diagonal, which means that you only need to read either the upper right or the lower left half of the table. Each cell within the matrix contains information about the correlation between a pair of variables. So let's focus first on the correlation between weekly disposable income and price paid for the album. In the top row of this cell, we can see that Pearson's R is 0.517. The second row tells us that this correlation coefficient is statistically significant at an alpha level of 0.05. And the third row just tells us that the figures reported in the previous two rows are based on a sample size of 65. By way of contrast, the correlation between price others would pay and weekly disposable income is 0.152 and is non-significant. Now, if you're having trouble visualizing the difference between a correlation of 0.517 and a correlation of 0.152, you can easily create a couple of scatter plots to compare them. And I did this earlier. So here is the first scatter plot. And if you ignore a few outliers above and below the main cluster of points, you can clearly see a positive linear association between price paid and weekly disposable income. So this is what a correlation of around 0.517 looks like. This is the second scatter plot. Here the correlation coefficient is 0.152. Although it's still possible to see a slight linear trend amongst these points, they're far more spread out. Anyway, if we go back up to the correlation matrix, you can see that the other four correlation coefficients are all significant at an alpha level of 0.05. Now, it's possible to report each of these correlation coefficients individually in a narrative style. Using the correlation between price paid and disposable income as an example, we might write the Pearson's product moment correlation between price paid for the album and weekly disposable income was strong and statistically significant. Note that the degrees of freedom here are n-2 and that the significance value is reported as less than 0.001 rather than equals 0.000. Usually though, we need to report several correlation coefficients at once, and this is best done in a table, and I've prepared an example for you here. You can see how reporting a set of correlations like this is much more efficient than reporting each one individually in a sentence. And yet this table contains just as much information as would be conveyed in 6 separate sentences. Now don't forget that when writing up your results, you may also need to note the results of any assumption tests you ran, and information on doing this can be found in StatHand.
First, we have the Between Subjects Factors table, which shows the number of students in each of the university courses. Next, the Descriptive Statistics table shows the mean and standard deviation of our dependent variable in each of the university courses. Below this, we have Levine's test of equality of error variances. This is used for testing the assumption of homogeneity of variance. As this is not significant, we can see that this assumption has been met. Next, the Tests of Between Subjects Effects table presents our main ANCOVA results. Here, we can see that the covariate, stress at the start of the year, is significantly related to our dependent variable, stress at the end of the year. Below this, we can see that even after controlling for stress at the start of the year, University course is also significantly related with our dependent variable. This table also contains the information that we need for the write-up. More specifically, the test statistic, which we denote with an italicized capital letter F, the degrees of freedom, which we denote with an italicized DF, and our significance level, or p-value. Below this, in the estimated marginal mean section, the estimates table presents the mean stress levels for each course after adjusting for the covariate. That is, if all participants had the same level of stress at the start of the year, these would be their mean levels of stress at the end of the year. The pairwise comparisons table below then shows which specific courses had significantly different levels of stress at the end of the year, which we can see here is medicine and dentistry. You could write up the findings like this. A one-way ANCOVA indicated that, after controlling for stress at the start of the year, university course had a significant effect on stress at the end of the year. You would then report your F statistics, DF, and p-value. You could then report the results of the post hoc testing from the pairwise comparisons table. Finally, you should also report an effect size. Information about how to do this is provided in StatHand.
When you run a bivariate regression using SPSS, you get several tables of output. The first table provides descriptive statistics for each variable in the regression. On average, people paid $5.92 for the album, and their weekly disposable income was $108.09. The second table of output is a correlation matrix. As we only have two variables in our regression, there's only one correlation coefficient reported here, 0.517, and that's statistically significant. The third table is called variables entered and removed. This table provides a summary of the variables in the bivariate regression. We can see here that just one predictive variable was entered into the regression, weekly disposable income, and that the criterion variable is price paid for the album. In the model summary table, there's a few different figures of interest. The first is R-squared, which indicates the proportion of variance in the criterion accounted for by the predictive variable. In this case, disposable income can account for 26.7% of the variance in prices that people paid for the album. By extension then, this leaves 73.3% of the variance in prices paid unaccounted for. It's possible that by including additional variables in this regression model, we could improve its predictive utility, and this is illustrated using standard regression and hierarchical regression in StatHand. Now, R-squared is a sample statistic and it tends to overestimate the true population effect. Consequently, it's recommended that you also report adjusted R-squared, which is said to be a better estimate of the proportion of variance in price paid that you could expect would be accounted for by disposable income in the population from which we've sampled. Here, the difference between the two figures is quite small anyway. Now, part of the purpose of regression is to build a model that can be used to make predictions. In this case, the model contains just one variable, weekly disposable income, and that's being used to predict the prices that customers paid for the album. Because the model is not perfect, and we already know that disposable income can't account for all of the variance in prices paid, then any predictions made with it will be off or inaccurate to some degree. The standard error of estimate is a measure of how much we'd expect predictions to be off on average. So on average, we would expect any predictions made using this model to be off on average by $2.91. Now, the ANOVA table reports the null hypothesis significance test for R-squared. The null hypothesis for this test is that R-squared does not depart from 0. And here we can reject this null hypothesis because the significance value is less than alpha, which we would typically set at 0.05. So in other words, R-squared departs significantly from 0. In the coefficients table, there are quite a few figures, although I'm not going to explain them all. Firstly, the constant is 2.616. This is the value that we would predict for the criterion, price paid, when the predictor, disposable income, is 0. Now you should be wary about interpreting this value if you haven't sampled around 0. And this is the case in this example. Everybody in our sample had at least $10 of disposable income each week. The unstandardized regression coefficient, or B, for disposable income is 0.031. For each unit or dollar increase in weekly disposable income, we would predict a corresponding $0.031, or if you like 3.1 cent, increase in the price a customer is willing to pay for the album. The corresponding t-test tells us that this regression coefficient departs significantly from 0. In other words, it's a significant predictor. It has predictive utility. Now the confidence interval around this unstandardized regression coefficient stretches from 0.018 to 0.043, so from 1.8 cents to 4.3 cents. Beta, or the standardized regression coefficient for disposable income, is 0.517. And this tells us that for every standard deviation increase in weekly disposable income, we would predict a 0.517 standard deviation increase in price paid. Now we'll skip over the residual statistics table and look at the charts. And these charts are used to assess the regression assumptions of normality, linearity, and homoscedasticity of residuals. Now the normality of residuals assumption can be assessed by looking at this histogram, and this plots the standardized residuals from smallest to largest. If this histogram conforms reasonably well to the normal distribution overlaid on top of it, as it does here, then we can conclude that the normality of residuals assumption has been met. Now, normality of residuals can also be assessed by looking at this normal PP plot of regression standardized residuals. Here, the normal distribution is represented by the diagonal line. The points on this plot should hug the line as closely as possible. Now, the last chart is a plot of standardized residuals against standardized predicted values, and it can be used to assess the assumptions of linearity and homoscedasticity of residuals. For a technical description of exactly what's being plotted here, please refer to some of the references in the StatHand app or website. For our purposes, if the distribution of points is roughly linear, so it's better captured by a straight line than anything else, we can conclude that the assumption of linearity of residuals has been met. Furthermore, if there's roughly the same amount of variability in the size of the residuals at all predicted values, then we can say that the assumption of homoscedasticity of residuals has been met. Now, putting aside the assumptions, which you can learn more about in StatHand, this is how you might summarize the results of these analyses. So bivariate regression indicated that weekly disposable income could account for a significant 26.7% of the variance in prices paid for the album. So when you run a chi-square test for goodness of fit in SPSS, you get two tables of output. The first is just a summary table of the data, and here we can see that 187 people chose the red soap, compared to 321 who chose the white, and 92 who chose the brown. Remember that if all three colours were equally popular, we would expect about 200 people to choose each colour, and these are the expected frequencies which are reported here. Now the final column of the first table reports the differences between the observed and expected frequencies, and these are referred to as residuals. The second table contains the chi-square test statistic and associated degrees of freedom and significance level. Here the significance level is less than 0.05, which we typically use as alpha, and we can thus conclude that the colour preferences we observed differed significantly from what would be expected in a situation where all three colours were equally popular. So we could write up our findings like this. The chi-square test for goodness of fit was statistically significant. The white soap was preferred by the largest number of shoppers, followed by the red and brown soaps. Now in a full write-up, you may also be expected to report on the assumptions of the test, as well as an effect size, and for this you can see StatHand for more information. When you run a chi-square test in SPSS, you get several tables of output. The first table can be ignored, and for now we'll skip over the second as well and look at the chi-square test table. If you have a very small sample and expected frequencies below 5, it's recommended that you interpret and report the likelihood ratio. Here we have 154 cases and no cells with expected frequencies below 5, and thus the Pearson chi-square test can be interpreted and reported. The Pearson chi-square statistic is statistically significant at the conventional alpha level of 0.05. This tells us that the two variables are related. However, it does not tell us how they are related or how strongly they are related. Looking at strength first, phi is an appropriate measure of effect size for a 2x2 design like ours. It is interpreted as a correlation coefficient with a lower limit of 0 and an upper limit of 1. By convention, a phi coefficient of 0.476 would be described as large or strong. In other words, there's a strong relationship between phone use behaviour and age. Next, we need to examine the nature of that relationship. This can be done by looking at the cross-tabulation table. Looking at the total sample, there were 46 adults and 108 teenagers observed using their phones. In other words, 29.9% of the sample were adults, and the remaining 70.1% were teenagers. Of the total sample, 65 or 42.2% were observed talking, and the rest were observed texting. Now we can look at the proportions of talkers versus texters in each age group. Looking at the adults first, we can see that over 3/4 of them were observed talking. This pattern is almost reversed amongst the teenagers, where only 1/4 of them were observed talking. At this point, and particularly in larger designs, it can be useful to look at the standardized residuals. They reflect the standardized differences between our observed cell frequencies and the cell frequencies we would expect if age and behavior were truly unrelated. Because they're z-scores, any standardized residual over plus or minus 1.96 is statistically significant at an alpha level of 0.05. For example, this standardized residual of 3.8 tells us that there were significantly more adults talking than would be expected if age and phone use behavior were unrelated. Similarly, the standard residual of 2.1 tells us that there were significantly more teenagers texting than would be expected if the two variables were unrelated. Finally, the means plot confirms and helps to visualize what we already know. Age and phone use behavior are related. Adults were more likely to talk, teenagers were more likely to text. And the results could be reported like this. When you run a Cochrane's Q test, the default display is quite minimal. However, it can be expanded to provide much more detail. Before that, though, let's work through this hypothesis test summary. So first we can see that a Cochrane's Q test was run, and that the null hypothesis for this test was that the distribution of TV news, newspaper, news website, and news radio are all the same. So in other words, the different types of media are all consumed by the same number of people. They're all equally popular. Now we're in a position where we can reject this null hypothesis because the significance level for the Q test is less than alpha, which has been set at 0.05 by default. Now if you double click the summary table, it will open up the model viewer. Now the table towards the bottom of the first screen tells you that there were 16 cases in the sample and that Cochrane's Q test statistic is 8.020. We'll need this for the reporting. We'll also need the degrees of freedom, which is 3, and you already know the significance level of 0.046. Now in the graph above this table, you can see the proportion of people who did and did not consume each type of media in the 24 hours prior to being polled. Now for some reason which is unclear to me, SPSS reverses the response categories in this graph. So green indicates the proportion of people who did not consume each type of media, rather than the people who did, as suggested in the legend. Looking at this graph, it appears as though TV news was consumed to a greater extent than the other three types of media. However, we will need to look at the pairwise comparisons before concluding that, for example, a significantly greater number of people watch TV news than listen to radio news. Before we get to that, though, I just want to confirm for you that the majority of the sample did watch TV news and did not listen to radio news, rather than the reverse, which is what this graph suggests. So in the View drop-down menu, I'm going to choose Categorical Field Information. So here I can see that about 2/3 of the sample watched TV news, and only about 1/4 of the sample listened to radio news. Now in the View menu again, select Pairwise Comparisons. And I'll just scroll down the page, and in this table, there's basically 6 McNamara tests reported. Each one is comparing just 2 levels of the independent variable. So for example, the first is comparing the proportions of people who did and did not consume news radio with the proportions of people who did and did not read news websites. And that comparison is non-significant. In fact, all of these comparisons are non-significant except for the one between news radio and television news. And by the way, you should read and report the adjusted significance levels in the final column rather than the ones in the column to the left of that. And this is because they've been adjusted to ensure that our family-wise type 1 error rate remains at 0.05, even though we've conducted 6 comparisons. Now this is how you might write up these findings. So the Cochrane's Q-test was statistically significant, and follow-up pairwise comparisons indicated that a significantly greater proportion of the participants consumed TV news than radio news. However, all other comparisons were non-significant. It might also be useful to include a graph indicating the proportion or number of people in the sample who consumed each type of media.
First, we have the ranks table here. In a Friedman ANOVA, all cases in the dataset are ranked and ordered, and then the average of these ranks for each condition is calculated. These are the mean ranks given here. We can see that the left composite face was often ranked higher than the right composite and control faces. In the table below, we have the information we need for the write-up. More specifically, we have the test statistic, chi-square, which we usually denote with an italicized Greek letter chi. We have the degrees of freedom, which is the number of conditions minus 1, and the significance level, or p-value, which is 0.027 here. You could write up the findings like this. A Friedman two-way ANOVA indicated that the rankings of emotional intensity were significantly different between the 3 face types. You would then report your chi-square value, degrees of freedom, and p-value. You should also report the mean rank for each condition from the ranks table above. Finally, you should also report an effect size. Information about how to do this is provided in StatHand. The first table to look at is the classification table for block 0. This is the block of the model with no predictors entered. Here, we can see that the model can correctly predict 66.7% of cases simply by predicting that no individuals had left. The omnibus test of model coefficients in block 1 shows how the model changed when the control variables were added. We can see that the chi-square value in the model row is not significant. This indicates that adding the control variables did not significantly improve the ability of the model to predict which employees would leave. Next, we have the Hosmer and Leemshow test. This assesses whether the model is significantly different to a good-fitting model. As the test is non-significant, our model would seem to fit the data reasonably well. The Block 2 omnibus tests of model coefficients show how the model changed when the variable of interest, job satisfaction, was added. We can see that the chi-square value is significant in the model row, which indicates that adding job satisfaction significantly improved the ability of the model to predict the employees that would leave. The model summary table underneath gives R-square equivalents for the logistic regression. Generally, both are reported. Under this, we have the classification table for the block with the control variables and the job satisfaction variable added. We can see that the new variable is 90% accurate, a clear improvement from the 66.7% accuracy of the model with no variables. Next, we look at the table for the variables in the equation. We want to look at the XB column for the significant predictors. This is what's called the odds ratio. This represents the change in probability of our outcome variable occurring. In this case, the change in probability of individuals leaving the workplace. A value of 1 means no change in probability. A value greater than 1 indicates that individuals are more likely to leave, while a value less than 1 indicates that individuals are less likely to leave. We can see that job satisfaction has an odds ratio of 0.076. This means that a 1 unit increase in job satisfaction is associated with a 92.4% decrease in the probability of individuals leaving the organisation. Below this, we have a plot of the observed groups and predicted probabilities. This is another means of assessing the fit or the accuracy of the model. Here, we can see that as the predicted probability of individuals leaving increased, the number of individuals that we observe leaving also increased. This indicates that our model has good predictive accuracy. When reporting these results, you would generally report the omnibus test of model coefficients, both R-square statistics, the Hosmer and Lemshow test, and the coefficients and confidence intervals from the variables in the equation table.
When you run a hierarchical multiple regression using SPSS, you get several tables of output. The first table provides descriptive statistics for each variable in the regression. So on average, people paid $5.92 for the album, their weekly disposable income was $108.09, they estimated that others would pay around $4.53 for the album, and they already owned between 4 and 5 previous albums. The second table is a correlation matrix. In the first column, we can see that all 3 predictors correlate substantially and significantly with the criterion. They also correlate to some extent with each other. The third table is called variables entered and removed. This table provides a summary of the variables in the regression. We can see here that there were 2 predictors entered into the regression on block 1, and SPSS refers to this 2 predictor model as model 1 throughout the output. On block 2, a third variable was entered. In total then, there are 3 predictors in model 2, the 2 which were entered on block 1, plus the third which was entered on block 2. Now looking at the top row of the model summary table, we can see that in combination, weekly disposable income and price others would pay accounted for 63.7% of the variance in price paid for the album. Scrolling down to the first part of the ANOVA table, the part which is labelled Model 1, we can see that this 63.7% is a significant proportion of variance. In combination, the 2 Block 1 predictors, which were disposable income and price others would pay, have predictive utility. Now looking back up at the model summary table, we can see that the 3 predictors in combination can account for 67.9% of the variance in price paid for the album. This 3 predictor model also has predictive utility. The difference between R squared for the 2 predictor model and R squared for the 3 predictor model is 0.042. To determine whether this proportion of incremental variance is statistically significant, we need to refer to the F-change test, and in this case, it is. So far we've learnt that weekly disposable income and price others would pay can, in combination, account for 63.7% of the variance in price paid for the album when entered on block 1 of the hierarchical regression. When the number of albums already owned was entered on block 2, it accounted for an additional 4.2% of the variance in price paid. This proportion of incremental variance was statistically significant. The full 3-predictor model was able to explain 67.9% of the variance in price paid. And again, this is a statistically significant amount. Refer to the section on standard multiple regression in StatHand for information about adjusted R-squared and the standard error of estimate. So next we'll scroll down to the coefficients table, which tells us about the role that each predictor plays in the regression. Generally speaking, we would only interpret the coefficients for the final model, in this case model 2. The partial unstandardized regression coefficient, or B, for disposable income is 0.021. For each unit or dollar increase in weekly disposable income, we would predict a corresponding $0.021 or 2.1 cent increase in the price a customer is willing to pay for the album. This is after controlling for or holding constant the other 2 predictors in the model. The corresponding t-test tells us that this regression coefficient departs significantly from 0. So in other words, it's a significant predictor. It has predictive utility. The other 2 partial unstandardized regression coefficients can be interpreted in the same way, and they are also statistically significant. The confidence intervals around each of these partial regression coefficients are reported to the right of the significance tests. Now, in addition to the unstandardized coefficients, there's also a set of standardized coefficients called beta. These indicate the standard deviation change in the criterion associated with a 1 standard deviation change in the relevant predictor, whilst controlling for any other predictors in the model. Now, also in the coefficients table, if we scroll to the right, we have a set of correlations. The 0-order correlations are the same as those reported in the correlation matrix at the top of the page. The part correlations can be squared to provide squared semi-partial correlations. A squared semi-partial correlation indicates the amount of unique variance in the criterion that can be accounted for by a predictor. If we square 0.325, which is the part correlation for disposable income in Model 2, we get 0.106. So in other words, disposable income can uniquely account for about 10.6% of the variance in prices paid for the album. And we already know that this is a statistically significant amount because we've already looked at the corresponding t-test. Now, on the far right of the coefficients table, we have a set of collinearity statistics. These are used to assess the absence of multicollinearity assumption which underpins multiple regression, and their interpretation is described in StatHand. In StatHand, you'll also find information about detecting outliers using the information which is provided in the residual statistics table. For now, though, we'll skip past this table. And finally, at the bottom of the output, there are 3 charts that can be used to assess the assumptions of normality, linearity, and homoscedasticity of residuals. Again, the interpretation of these is described in StatHand. Now, this is how you might summarize the results of these analyses. So on block 1 of a hierarchical multiple regression, weekly disposable income and the estimated prices that others would pay accounted for a significant 63.7% of the variance in the prices customers paid for the album. When the number of albums the customer already owned was entered on block 2, it accounted for an additional and significant 4.2% of the variance in prices paid. In total, the 3 predictors accounted for a significant 67.9% of the variance in prices paid. As illustrated in Table 1, all 3 predictors accounted for a significant proportion of unique criterion variance in the final regression model. Now, in a full write-up, you would also need to include the results of your assumption tests, and these are described in StatHand.
First, we have the ranks table here. This shows the number of students for each condition, N, and the mean rank for each condition. In a Kruskal-wallis ANOVA, all cases in the dataset are ranked and ordered, and then the average of these ranks in each group is calculated. Because the mean ranks appear to be relatively similar between conditions, this indicates that all groups had similar mixes of low, middle, and high ranking grades. In the table below, we have the information we need for the write-up. More specifically, the test statistic, which we would denote with an italicized Greek letter chi, the degrees of freedom, which is the number of conditions minus 1, and the significance level, or p-value, which is 0.877. You could write up the findings like this. A Kruskal-wallis one-way ANOVA indicated that there were no statistically significant differences in the grades assigned to the control, poor, and bright students by the teachers. You would then report your chi-square value, degrees of freedom, and p-value. You should also report the mean rank for each condition from the ranks table above. Finally, you should report an effect size. Information about how to do this is provided in StatHand.
When you run a Mann-Whitney test in SPSS, the default display is quite minimal. However, it can be expanded to provide more detail. Before that though, let's work through this hypothesis test summary table. So here we can see that an independent samples Mann-Whitney U test was run, and the null hypothesis for this test was that the distribution of academic level is the same across categories of gender. So in other words, there are the same number of male associate lecturers and so on as there are female associate lecturers and lecturers. So we're in a position where we can reject this null hypothesis because the significance level for the test is less than alpha, which has been set at 0.05 by default. So double-click on the summary table to open up the model viewer. Now the graph at the top here indicates that females tend to be clustered further down the scale of academic levels than males, and the males have a higher mean rank, indicating that they appear more frequently in the higher ranked academic positions. Now in the table below the graph, we have the information that we need for the write-up. So most specifically, we've got the Mann-Whitney U value, which is 185.5. We've got the standardized test statistic of negative 2.547, and the significance level, which is 0.011. So you could write up your findings like this. A Mann-Whitney U test indicated on average that the academic levels of the male participants significantly exceeded those of the female participants. Now additionally, you should also report an effect size and the results of your assumption tests. And information on how to do this is provided in StatHand. Two tables of output are provided by SPSS. In the first, we can see that 42 people were in favour of stem cell research before watching the documentary and remained in favour of this type of research after the documentary. 52 people were initially against stem cell research and remained so after the documentary. 84 people were initially against the research and then changed their minds after watching the documentary, and the remaining 22 people also changed their minds, but did so in the opposite direction. In the second table, we have a chi-square statistic and associated significance level. As this significance level is less than 0.05, and referring back to the numbers in the first table, we can conclude that significantly more participants altered their attitudes in favour of stem cell research than against stem cell research. And you could report the findings like this. So slightly over half of the sample changed their views on embryonic stem cell research after watching a persuasive documentary on this topic. Of these, significantly more participants changed their views from negative to positive than from positive to negative.
First, we have a summary of the number of individuals in each category of the dependent variable, which here is the number of individuals which prefer each political party. Below this, we have the model fitting information table. This tests whether our model fits significantly better than a model that has no predictors. We can see here that our model does fit significantly better. The pseudo R-square table underneath gives R-square equivalents for the logistic regression. Generally, all are reported. Next, we have the likelihood ratio tests for each predictor in the model. For each predictor, we have the log likelihood of the model with that predictor removed, and whether this is significantly different to that of the full model. In effect, this can show us how necessary each of the predictors are. Here, we can see that the model fit does not significantly change when income is removed as a predictor. Next, we look at the table of parameter estimates. We want to look at the XB column for each of the significant predictors. This is what's called the odds ratio, and it represents the change in probability of the reference category of our outcome variable occurring. In this case, the change in the probability of individuals voting for the Labour Party. A value of 1 means no change in probability. A value greater than 1 indicates that individuals are more likely, while a value less than 1 individuals are less likely. We can see that neither age nor income altered an individual's likelihood to vote for the Greens instead of Labour. However, we can see that for each 1 year increase in age, individuals become 9.4% more likely to vote for the Liberals over the Labour Party. When reporting the results, you would generally report the model fitting information, R-square statistics, and the coefficients and confidence intervals from the variables in the equation table.
When you run a one-sample t-test in SPSS, you get two tables of output. The first table provides descriptive statistics for the sample. So here we can see that there were 28 students in the class and that their mean test score was 75.54. This is the value that we will be comparing with the national average of 86.4 using the one-sample t-test. You can also see that the sample's test scores varied around this mean by an average of 5.568 points. This is the standard deviation. At the top of the second table, the test value of 86.4 is displayed. This is the value that we're comparing the sample mean with. Always check that this figure is correct before reading the rest of the table. So next, reading across the table from left to right, we have the results of the t-test, which is statistically significant because the two-tailed significance level is less than alpha, which we typically set at 0.05. This allows us to reject the null hypothesis for the one-sample t-test, which is that there is no difference between the sample mean and the test value. So in other words, there is a statistically significant difference between our sample mean of 75.54 and the test value, which is the national average literacy score of 86.4. The raw difference between these two values is negative 10.864, which is displayed in the mean difference column. And the 95% confidence interval around that mean difference ranges from negative 13.02 through to negative 8.71. So to report this finding, we might say something like, a one-sample t-test indicated that the 28 students had an average literacy test score 10.86 points lower than the national average of 86.4. This difference was statistically significant at an alpha level of 0.05. Now note that even though the significance value is reported as 0.000 by SPSS, you should use less than 0.001 in your reporting. Also note that if your research hypothesis was directional, you can divide the p-value in half and report the test as one-tailed. And finally, don't forget that when writing up a piece of research like this, you may also be required to report the results of your assumption testing and an effect size. And you can refer to StatHand for more information about these. When you run a one-sample Wilcoxon test, the default display is quite minimal. However, it can be expanded to provide more detail. Before that though, let's work through this hypothesis test summary table. So here we can see that a one-sample Wilcoxon-signed rank test was run, and the null hypothesis for this test was that the median sale price equals 382,000. We're in a position where we can reject that null hypothesis because the significance level for the test is less than alpha, which has been set at 0.05 by default. So you can double-click the summary table and that will open up the model viewer. Now in the graph at the top of the screen, we can see the distribution of sample property sales prices. As we noted in the previous video, this is positively skewed, with most sales going for less than 500,000 and just a handful for over $1 million. On this graph, we can also see both the sample median property price in blue, which is 437,500, and the median that we're comparing that value to in green, which is 382,000. We already know that these two values differ significantly, and this is reconfirmed by looking at the significance value at the bottom of the table. In this summary table, we also have the other values that we'll need for the write-up. So most specifically, the test statistic, which we usually denote with an italicized capital T. SPSS produces quite a lot of output. However, not all of it needs to be interpreted. In the descriptives table, we can see that there were 8 dogs in each group. The mean jumping time for the no escape group is clearly higher than the means for the other 2 groups. However, we need to look at the results of our statistical tests before we can conclude that this difference is more than just sampling error. In the descriptives table, we also have standard deviations and standard errors for each group, 95% confidence intervals around each mean, and minimums and maximums. In the test of homogeneity of variances table, we have the results of Levene's test. This test tests the null hypothesis that the 3 group variances are approximately the same, or homogeneous. We do not want to reject this null hypothesis, and so we want the significance value here to be greater than 0.05, which it is. So in other words, we can assume homogeneity of variances. And this means that we can ignore the output for the Welsh and Games-Howell tests that we requested earlier. The next table down reports the results of the one-way ANOVA. Here, we're testing the null hypothesis that the 3 group means are approximately the same. As the significance level here is less than 0.05, we're able to reject this null hypothesis and conclude that the group means are not all the same. But that's all we can do. At this stage, we do not yet know specifically which means differ. To find this out, we need to look at the results of the Tukey post hoc tests. The degrees of freedom, F ratio, and significance levels should be noted down, as they'll be required for your results. The robust tests of equality of means table can be ignored, as homogeneity of variance is assumed. Likewise, the Games-Howell section of the multiple comparisons table can be ignored. Instead, we'll focus on the Tukey HSD or honestly significant difference section. Here, we have 3 pairwise comparisons. Each of these can be evaluated for significance at an alpha level of 0.05, as their significance levels have been automatically corrected for type 1 error inflation by SPSS. The first compares the means for the escape and no escape groups, and it's statistically significant at an alpha level of 0.05. The mean difference is negative, telling us that the no escape group had the larger mean. The second pairwise comparison is between the escape and control group means. This comparison is non-significant at an alpha level of 0.05. The 2 means do not differ by any more than would be expected by chance. The final pairwise comparison is between the no escape and control group means. This is significant, and the positive sign of the mean difference, calculated as no escape minus control, tells us that the no escape condition had the larger mean. In other words, the animals in the no escape group took significantly longer, on average, to jump the barrier after the light was turned on. We can report these findings as t-tests, where t is the mean difference divided by the standard error of difference. The degrees of freedom are the within groups degrees of freedom from the ANOVA table, which is 21 in our case, and the p-value can be read directly from this table. The homogeneous subsets table contains the same information as the multiple comparisons table. The control and escape conditions are in the same subset, which indicates that they do not differ from each other. And they both differ from the no escape group, which is in a different subset. And finally, if you're not comfortable with reading direction from the means table, you can simply interpret the means plot. The no escape group took significantly longer to jump the barrier than the other two groups. The escape and control groups did not differ by any more than would be expected by chance. To report these findings, we might say something like this. Now don't forget that when writing up a piece of research like this, you may also be required to report the results of your assumption testing and effect sizes. Effect sizes are necessary for interpretation as they give the reader a sense of the magnitude of each of the effects that you report. When you run a paired samples t-test in SPSS, you get 3 tables of output. The first table provides descriptive statistics for each set of scores. Looking at this table, we can see that there were 15 participants in this study, and when exposed to the control stimulus, they responded on average within 422.6 milliseconds. When they were exposed to the experimental stimulus, they responded on average within 320.8 milliseconds. Although these two means certainly differ, a null hypothesis significance test, in this case a paired samples t-test, is required to determine whether or not they differ by more than would be expected by chance. The second table reports the Pearson's correlation between the two sets of scores. At 0.499, this correlation is positive and quite strong, as we would predict. Participants who responded quickly during the control trials also responded quickly during the experimental trials. Participants who were slower during the control trials also tended to be slower during the experimental trials. Typically, we can ignore this second table and we can focus our attention on the third. In the first part of this table, we can see that the difference between the two means is 101.8 milliseconds. And if we look to the right, we have the results of the paired samples t-test. The null hypothesis for this test is that the difference between the two means is actually 0. As the t-test here is statistically significant, because the significance level is less than 0.05, we can reject this null hypothesis. So in other words, the two condition means differ by more than would be expected by chance alone. And to report this finding, we might say something like, using a paired samples t-test, we found that participants' mean reaction times in milliseconds to virtual cyclists wearing fluorescent vests were significantly faster than their reaction times to virtual cyclists wearing non-fluorescent vests during a computer-based nighttime driving simulation. Note that even though the significance value is reported as 0.000 by SPSS, you should use less than 0.001 in your reporting. Also note that if your research hypothesis was directional, you can divide the p-value in half and report the test as one-tailed. Finally, don't forget that when writing up a piece of research like this, you may also be required to report the results of your assumption testing, an effect size, and a confidence interval around the mean difference. The confidence interval is reported by SPSS, but you'll need to run your assumption tests and calculate an effect size separately. And you can find advice on doing this in StatHand. Principal components analysis is a complex topic, and when you run one in SPSS, you get a lot of output. Some of this output is used to assess whether or not the data are suitable for principal components analysis, whereas some of it presents the results of the actual analyses. I'll provide you with a quick overview of the key points to consider, but for further information you should consult some of the references on the StatHand website or app. So the first table of output is a correlation matrix, and in the top portion you can see the intercorrelations amongst participants' responses to the 5 items. So there's a number of substantial looking correlations here. So for example, the correlation between adventure and novelty is 0.709. A number of substantial correlations in the matrix suggest that the data, or more specifically the correlations between variables, can be summarized with one or more components. If all of the correlations in this matrix are close to 0, then you should be wary about running PCA, as you're likely to extract as many components as you have items. Underneath the correlation matrix is the determinant. This is an indicator of multicollinearity. It should be greater than 0.00001, which it is here. Now the second table contains the Kaiser-Meyer-Olkin measure of sampling adequacy and Bartlett's test of sphericity. These are additional measures that we can use to check that the data is suitable for principal components analysis. It's recommended that the KMO be above a minimum of about 0.6 and Bartlett's test be significant. Now here the KMO is almost 0.6, so I think we'll call it good enough. For information about how to interpret these statistics, you can consult some of the references in StatHand. The third table is called anti-image matrices. The only thing that you need to check in this table are the measures of sampling adequacy that run down the diagonal of the second part of the table. These figures indicate the degree to which each item is correlated with all of the others in the correlation matrix. Ideally, all of these individual measures of sampling adequacy should be above about 0.5 or 0.6. Any items with measures of sampling adequacy below this should be considered as potential candidates for removal from the scale. Here, they're all above the 0.5 threshold, although some are only just above. Now the next table, if we scroll down, is a table which reports the initial and the extracted communalities. The initial communalities represent the total proportion of variance in each item, which is always going to be 1. The extracted communalities indicate the proportion of variance in each item, which can be accounted for by the extracted components in combination. The higher these figures are, the better. Now the next table down is the total variance explained table, and it tells us how many components have been extracted using principal components analysis. Remember, the rule that we set for extracting components was the Kaiser criterion, which says that we should extract components with initial eigenvalues greater than 1. For the logic of why we do this, refer to some of the references which are listed in StatHand. Here, there are 2 initial eigenvalues greater than 1, and thus 2 components have been extracted. And the decision to extract 2 components is confirmed by the scree plot, where you can see that there are 2 eigenvalues which clearly stand out above the other 3. So now we know that 2 components have been extracted. The next question to ask is, what do these 2 components actually look like? And to answer this question, we need to keep scrolling. For now, we'll scroll past the component matrix and the reproduced correlations matrix, and we'll stop at the pattern matrix. When you run an oblique rotation, this is generally the table that you'll be looking at to interpret your components. It contains what we commonly refer to as loadings. Now I've organized this table to make it easy to interpret, and I've done that by sorting the loadings by size and by hiding very small loadings, so loadings which are under 0.3. Now we can see that 3 items load onto component 1, and all of these items appear to be about pragmatic or practical issues. So I might label this component something like practical considerations. Now the remaining 2 items load onto the second component. These items appear to be about pleasure or enjoyment, so I might label this component something like pleasure considerations. We can scroll past the structure matrix now, and we'll have a look at the component correlation matrix. This tells you the correlations between components. So here we've extracted 2 components, so there's only one correlation that we need to focus on, and that correlation is negative 0.178. Now, as a rule of thumb, if the correlations between components are greater than about 0.3 on average, then an oblique rotation like direct oblement is more appropriate. If all the correlations between components are small, then oblique and orthogonal rotations will produce very similar solutions. Now, if you want to try an orthogonal rotation and compare the two, you just need to repeat the steps that I described in the previous video, except choose Verimax instead of direct oblement in the rotation dialog. And then, when interpreting the results, look for the rotated component matrix rather than a pattern matrix. So finally then, we should get a sense of whether our two-component model is a good model. And there are a number of things that we can do, that we can look at to do this, including, for example, looking at the proportion of variance accounted for by the extracted components in combination. And in our case, that's 72.65%. We can also look at the extracted communalities, and we can look at the interpretability of the pattern matrix. We can also, though, look at the reproduced correlation matrix to get a sense of goodness of fit. So essentially, we've used a correlation matrix, which was the first table of output right at the top of this page, to develop a two-component model. Now, if this two-component model is a good model, we should be able to use it to reproduce the original correlation matrix. And this is what we've done in the first part of the table that we're looking at on the screen. These are SPSS's best estimates of the correlations between items based on the two-component model. In the second part of the reproduced correlations table, we have what are called residuals. The residuals are the raw differences between the original correlations and the reproduced correlations. And the smaller the residuals, the better the model. Now, as a rule of thumb, we want the majority of these residuals to be trivial. Generally speaking, if fewer than 60% of them have absolute values greater than 0.05, we can argue that the model has done a reasonable job of reproducing our original correlation matrix. And here, it looks like we've just met that threshold. Now, when you write up a principal components analysis, there's quite a lot of information that needs to be reported. So in this case, what you would need to do is firstly explain how the 5 items were subjected to principal components analysis and that you used oblique rotation. And then we'd explain how we tested univariate normality and bivariate linearity, and there's advice on how to do this in StatHand. And we'd also want to report what we found here. We'd report on the checks that we looked at earlier in this video. So the bivariate correlation matrix indicated a number of substantial correlations. The individual measures of sampling adequacy were all above 0.5, as was the overall Kaiser-Meyer-Olkin measure of sampling adequacy. We'd also report that Bartlett's test was statistically significant and that the determinant was 0.238. And we'd need to explain how two components were extracted and could, in combination, account for 72.65% of the variance in the data. And we then report the pattern matrix in a nicely formatted table and make sure that we named each of the components in that table. And we'd also provide some evaluation of goodness of fit, so making reference to any unusually low communalities, making reference to the percentage of redundant residuals, and so on. So as I've said previously, there's a lot that you need to take into consideration when running principal components analysis. Take your time and use the resources that you have available to you, including those that we have listed on StatHand. When you run a standard multiple regression using SPSS, you get several tables of output. The first table provides descriptive statistics for each variable in the regression. On average, people paid $5.92 for the album, their weekly disposable income was $108.09, and they estimated that others would pay around $4.53. The second table, which I'll just scroll down to, is a correlation matrix. In the first column, we can see that both predictors correlate substantially with the criterion. In the second column, though, we can see that they do not significantly correlate with each other. The third table is called Variables Entered and Removed. This table provides a summary of the variables in the regression. We can see here that there were two predictors entered into the regression together, These were price others would pay and weekly disposable income. And below the table we can see that the criterion variable is price paid for the album. In the model summary table, there's a few figures of interest. The first of these is R², which indicates the proportion of variance in the criterion accounted for by the predictor variables in combination. In this case, disposable income and price others would pay can collectively account for 63.7% of the variance in prices that people paid for the album. Now, R² is a sample statistic and it tends to overestimate the true population effect. Consequently, it's recommended that you also report adjusted R², which is said to be a better estimate of the proportion of variance in price paid that would be accounted for by the two predictors in combination in the population from which we've sampled. Here, though, the difference between the two figures is quite small anyway. Now, part of the purpose of regression is to build a model that can be used to make predictions. In this case, the model contains two variables, weekly disposable income and price others would pay, and these are being used to predict the prices that customers paid for the album. Because the model's not perfect, and we already know that these variables can only account for about 64% of the variance in prices paid, any predictions made with it will be off or inaccurate to some degree. The standard error of estimate is a measure of how much we'd expect predictions to be off on average. So on average, we would expect that any predictions made using this model will be off by an average of $2.07. The ANOVA table reports the null hypothesis significance test for R². The null hypothesis for this test is that R² does not depart significantly from 0. Here we can reject this null hypothesis because the significance value is less than alpha, which we typically set at 0.05. So in other words, R² departs significantly from 0. In combination, the predictors can account for a significant proportion of the variance in prices paid for the album. In the coefficients table, there's quite a few figures. I'm not going to explain them all. Firstly, we'll look at the constant, which is negative 0.279. So this is the value we would predict for the criterion, price paid, when both predictors are fixed at 0. You should be wary about interpreting this value, though, if you haven't sampled around 0 on all variables. The partial unstandardized regression coefficient, or B, for disposable income is 0.025. For each unit or dollar increase in weekly disposable income, we would predict a corresponding $0.025 or 2.5 cent increase in the price a customer is willing to pay for the album after controlling for or holding constant the other predictors in the model. Now, the corresponding t-test tells us that this regression coefficient departs significantly from 0. So in other words, weekly disposable income is a significant predictor. It has predictive utility. The partial unstandardized regression coefficient for price others would pay is 0.771. If we hold disposable income constant, we would predict that a $1 increase in the estimated price others would pay would correspond to a 77.1 cent increase in the price that participants would pay for the album. And looking at the relevant t-test, we can see that this predictor is also statistically significant. Now, the confidence intervals around each of these partial regression coefficients are reported to the right of the significance tests. Now, in addition to the unstandardized coefficients, we also have a set of standardized coefficients called beta. These indicate the standard deviation change in the criterion associated with a 1 standard deviation change in the relevant predictor, whilst controlling for any other predictors in the model. Also in the coefficients table, we have a set of correlations. The zero-order correlations are the same as those reported in the correlation matrix above, the correlations between each predictor and the criterion. The part correlations can be squared to provide squared semi-partial correlations. A squared semi-partial correlation indicates the amount of unique variance in the criterion that can be accounted for by a predictor. If we square 0.419, which is the part correlation for disposable income, we get 0.175. So in other words, disposable income can uniquely account for about 17.5% of the variance in prices paid for the album. And we already know that this is a significant amount because we've already looked at the corresponding t-test. Now on the far right of the coefficients table, we have a set of collinearity statistics. These are used to assess the absence of multicollinearity assumption underpinning multiple regression, and their interpretation is described in StatHand. In StatHand, there is also information about detecting outliers using the information in the residual statistics table. For now, though, we'll skip past this. And finally, there are 3 charts that can be used to assess the assumptions of normality, linearity, and homoscedasticity of residuals. Again, the interpretation of these is described in StatHand. So this is how you might summarize the results of these analyses. To estimate the proportion of variance in prices that customers would pay for the album using both weekly disposable income and customers' estimates of what others would pay, standard multiple regression was used. In combination, the 2 predictors could account for a significant 63.7% of the variance in prices paid for the album. As illustrated in Table 1, both predictors account for a significant proportion of unique criterion variance. In the full write-up, you would probably also need to include the results of your assumption tests, and these are described in StatHand. So when you run a Wilcoxon-signed rank test in SPSS, the default display is quite minimal. However, it can be expanded to provide more detail. Before that though, let's work through this hypothesis test summary table. So here we can see that a related samples Wilcoxon signed rank test was run, and the null hypothesis for this test was that the median of differences between the before and after rankings is equal to 0. So in other words, that GM ingredients were ranked the same at both points in time. Now we're in a position where we can reject this null hypothesis because the significance level for the test is less than alpha, which has been set at 0.05 by default. So double click on the summary table to open up the model viewer. Now the graph at the top here is a bit misleading, and so we'll skip over it. But in the legend to the side, it's interesting to note that 6 people ranked the GM ingredients as less important after the lecture, 22 ranked them as more important after the lecture, and the remaining 12 gave the same ranking at both points in time. In the table below, we have the information that we need for the write-up. Most specifically, we've got the test statistic, which we usually denote with an italicized capital T, the standardized test statistic, which is represented with an italicized lowercase z, and the significance level, which is 0.001. So you could write up the findings like this. A Wilcoxon signed rank test indicated that, on average, participants ranked GM ingredients higher in importance after attending the lecture than they did before. You should also indicate the number of positive and negative differences and the number of ties somewhere, in addition to the median rank for both sets of scores. Those median ranks can be derived from the Explore option under Descriptive Statistics in the Analyze menu, which is here. And finally, you should report an effect size, and information about how to do this is provided in StatHand. When you run an independent samples t-test in SPSS, you get 2 tables of output. The first table provides descriptive statistics for each group of scores. Here we can see that there were 18 members of the male group and 17 members of the female group. Although the 2 group means are very similar, there is more variability in the male group, as indicated by the larger standard deviation. The second table actually contains 2 separate tests. The first test is Levene's test for equality of variances. The null hypothesis for this test is that the 2 group variances are homogeneous, or the same. In other words, it's a test of the homogeneity of variances assumption. When Levene's test is significant, as it is here with a significance level of less than 0.05, the homogeneity of variances assumption has been violated. Consequently, we need to report and interpret the t-test for equal variance is not assumed, which is also called Welch's t-test. The null hypothesis for this test is that the two group means are the same. As the test is not significant, because the significance level is greater than 0.05, we are unable to reject the null hypothesis. In other words, the two group means do not differ by more than would be expected by chance. To report this finding, we might say something like, Welch's t-test was used to compare the mean IQ scores of the male and female students. The mean difference of 0.79 was not statistically significant. The 95% confidence interval simply tells us that the true population mean difference is probably somewhere between negative 5.03 and 6.6. Also note that if your research hypothesis was directional, you can divide the p-value in half and report the test as one-tailed. Don't forget that when writing up a piece of research like this, you may also be required to report the results of your assumption testing and an effect size. Factor analysis is a complex topic, and when you run factor analysis in SPSS, you get a lot of output. Some of this output is used to assess whether or not the data are suitable for factor analysis, whereas some of it presents the results of the actual analyses. I'll provide you with a quick overview of the key points to consider, but for further information you should consult some of the references on the StatHand website or app. The first table of output is a correlation matrix. In the top portion you can see the intercorrelations amongst participants' responses to the 12 items on the humour questionnaire. There are a number of substantial looking correlations here. So for example, the correlation between item 1, which is I like to make fun of others, and item 5, which is I frequently make others the target of my jokes, is 0.749. A number of substantial correlations in this matrix suggest the presence of one or more underlying factors. If all of the correlations in this matrix are close to 0, you should be wary about running factor analysis, as you're likely to extract as many factors as you have items. Now, underneath the correlation matrix is the determinant, and this is an indicator of multicollinearity. If it's higher than 0.00001, as it is here, then multicollinearity is not a problem. Now, the second table, which I'll just scroll down to, contains the Kaiser-Meyer-Olkin measure of sampling adequacy and Bartlett's test of sphericity. These are additional measures that we can use to check that the data are suitable for factor analysis. It's recommended that the KMO be above a minimum of about 0.6 and Bartlett's test be significant, which they are here. And for information on how to interpret these statistics, please consult some of the references in StatHand. Now, the third table is called the anti-image matrices. And the only thing that you need to check in this table are the measures of sampling adequacy which appear to run down the diagonal of the second part of the table. So these figures indicate the degree to which each item is correlated with all of the others in the correlation matrix. Now, ideally, all of these individual measures of sampling adequacy should be above about 0.6. And any items with individual measures of sampling adequacy below this should be considered as candidates for removal from the scale. Now here, they're all above our 0.6 threshold. Now the next table reports the initial and extracted communalities. Initial communalities represent the proportion of shared variance in each item. The initial communality for item 1, for example, is 0.690, and this means that 0.69 of the variance in item 1 can be accounted for by the other 11 items in combination. And obviously, the higher these values are, the better. Now, the extracted communalities indicate the proportion of shared variance in each item, which can be accounted for by the extracted factors in combination. And again, the higher these figures are, the better. Now, if you look at item 7, it has a low initial communality, indicating that only 28% of its variance can be accounted for by the other variables in combination. Furthermore, only a small amount of that shared variance, 21.5%, can be accounted for by the extracted factors. So in other words, the extracted factors are doing a poor job of predicting how participants respond to this item. And this means that we should keep a close eye on this item, item 7, as we continue reading through the output. Now, the total variance explained table tells us how many factors have been extracted using principal axis factoring. Now, remember the rule that we set for extracting factors was the Kaiser criterion. And the Kaiser criterion says that we should extract factors with initial eigenvalues greater than 1. For the logic of why we do this, refer to some of the references listed in StatHand. Now here there are 2 initial eigenvalues greater than 1, and thus 2 factors have been extracted.
In the data file, we have 4 variables of interest. First, whether or not the employee has left the workplace, their level of job satisfaction and workload, and whether or not they were a full-time employee. We can see that our outcome variable, whether or not the employee has left, is a nominal or dichotomous variable. If I change to the data view, I can see that the first employee did not leave the workplace, had a job satisfaction level of 3 and a workload level of 6, and was not working full-time. To conduct the logistic regression, we go to Analyze, Regression, Binary Logistic. First, we move our dependent variable, whether the employee has left, into the dependent field. Then we move all of our predictors into the covariates field. Now we need to give SPSS a bit of information about our categorical predictors. Now we only have one, whether or not the employee was full-time or not. We move this variable into the categorical covariates field, and then we tell SPSS that our reference category or control group is the first category. Click Continue to close this menu. Next, we open up the Options menu. We want to select Classification Plots, the Hosmer-Lemeshow Goodness of Fit Test, Case-wise Listing of Residuals, and CI for XB. Click Continue to close this menu, and then OK to run the logistic regression.
In this video, we'll use SPSS to run a bivariate regression. Specifically, we'll use disposable income to predict the amount that customers chose to pay for a record which they were able to set their own price for. Now, although there are several variables in this data file, for this exercise we'll only be using the first 2. Price paid for the album, which is the criterion or dependent variable, and weekly disposable income, which is the predictor or the independent variable. Now these are both ratio variables, and we're seeking to predict or account for variance in one, price paid, with knowledge of the other, disposable income, and consequently bivariate regression is an appropriate analytic technique. Now if we move across to the data view, you can see that in total there are 65 cases in this data file. So in the Analyze menu, select Regression and then Linear. Move the criterion variable, which is price paid for the album, into the dependent list, and move the predictor, which is weekly disposable income, into the independence list. In the statistics dialog, select confidence intervals and also descriptives, and click Continue. And in the plots dialog, select ZPRED, which stands for standardized predicted values, and move that into the X field, and select ZResid, which stands for standardized residuals, into the Y field. Select histogram and normal probability plot, and then click Continue. And to finish, you can click OK. And the output will appear in the SPSS Output Viewer. So firstly, I'm going to switch to the Value Labels view so you can see which colours the participants actually selected. Now scrolling down the data file, you can see that some shoppers chose white soap, whilst others chose red or brown soaps. And in total, there are 600 cases in the data file. Now, if all three colours are equally popular, we'd expect approximately 200 people to choose each colour, and this is my null hypothesis. So using a chi-square test for goodness of fit, we'll ask whether the actual observations differ from what would be expected under this null hypothesis. So in the Analyze menu, select Non-Parametric Tests, and then Legacy Dialogues, and chi-square. Now the test variable is colour, so we'll move that across into the test variable list. And under expected values here, I'm going to specify all categories equal. And this will allow me to compare the distribution of observed colour preferences with the distribution that would be expected if all three colours were equally popular. As an alternative though, it is possible to specify an unequal distribution, and you can refer to the SPSS Help menu for further information about this feature. For now though, we'll click OK, and our output will appear in the SPSS viewer. 154 people were covertly observed using their mobile telephones at a local supermarket. Each was classified as either an adult or a teenager, and their phone use behaviour was categorised as either talking or texting. These data will be used to test the hypothesis that phone use behaviour is related to age. In the SPSS data file there are two columns. The first column records which age group each case belongs to, and the second records their behaviour. As both variables are nominal, they require value labels, and these have been added in the variable view. For age, 1 has been used to represent members of the adult group, and 2 has been used to represent teenagers. For behaviour, 1 represents talking, and 2 represents texting. Back in the data view, we can see that the first case is a teenager who was observed texting. The third is an adult who was observed talking. To address the hypothesis that phone use behaviour is related to age, we'll use a chi-square test of contingencies. With this test, we'll ask, is category membership on one nominal variable, for example phone use behaviour, contingent on category membership on a second nominal variable, for example age? In the Analyze menu, select Descriptive Statistics and then crosstabs. Move one variable into the Rows field and the other into the Columns field. In the Statistics dialog, select chi-square and find Kramer's V. Click Continue. In the Cells dialog, select Observed and Expected Counts, Row, Column and Total Percentages, and Standardized Residuals. Click Continue. Select Display Clustered Bar Charts, and now click OK. In the data file, we have a variable set up for each of the 4 types of media. These variables have been used to indicate whether or not each participant consumed each type of media in the previous 24 hours. Now, if we swap to the data view, I can see that participant number 1 consumed television news and also radio news in the 24 hours prior to being polled, whereas participant 2 consumed TV news, newspapers, and radio, and so on. So in the Analyze menu, select Non-Parametric Tests. Now there are 2 ways that we can run a Cochrane's Q test. Firstly, we can use the legacy dialogues, and in this case, the relevant option is K-related samples, which is just off the bottom of the screen. or we can use the new non-parametric model builder. I'm going to use the latter because it will give me the option of outputting follow-up pairwise comparisons in addition to the omnibus Q-test. So select Related Samples, and then in the Fields tab, select the 4 levels of the independent variable and move them into the Test Fields list. Now it's important here that the data type has been correctly specified as nominal in the data editor's variable view. Now under the Settings tab, you can leave the default as automatically choose the tests based on data, and a Cochrane's Q-test will be produced. But I think it's better practice to know exactly what you're running before you actually run it. So I'm going to select Customize Tests, and then I'm going to tick Cochrane's Q. And under multiple comparisons, we can leave the default as all pairwise selected. So if you click Run, your output will appear in the viewer.
In the data file, we have a variable set up for the ranks given to the left composite face, for the right composite face, and for the control face. If I swap to the data view, I can see that the first participant rated the left composite face first, the control face second, and the right composite face third. To analyse this data using a Friedman two-way ANOVA, we go to the Analyze menu, Non-Parametric Tests, Legacy Dialogues, and K-Related Samples. Now we want to move all of the face variables into the test variable field. Make sure that Friedman is selected in the test type field and click OK to run the ANOVA. And you will see the output pop up in the SPSS output window like this.
In the data file, we have 4 variables of interest. First, whether or not the employee has left the workplace, their level of job satisfaction and workload, and whether or not the employee was full-time. We can see that our outcome variable, whether or not the employee has left the workplace, is a nominal or dichotomous variable. If I change to the data view, I can see that the first employee did not leave the workplace, had a job satisfaction level of 3, a workload level of 6, and did not work full-time. To run the hierarchical logistic regression, we go to Analyze, Regression, Binary Logistic. First, we move our dependent variable, whether or not the employee left, into the dependent field. Then we move our control variables, workload, and whether or not the employee was full-time, into the covariates field. Next, we click the Next button, and we add our variable of interest, job satisfaction. Now we need to give SPSS a bit of information about our categorical predictors. So we open up the categorical menu, and we only have one, whether or not the employee was full-time. We move this into the categorical covariates field, and we set the reference category or control group as the first group. Click Continue to close the menu. Next, open up the Options menu, and we want to select Classification Plots, Osmer-Leem Show Goodness of Fit, Case-wise Listing of Residuals, and CI for XB. Click Continue to close the menu, and OK to run the logistic regression.
In this video, we'll use SPSS to run a hierarchical multiple regression. The criterion or the dependent variable is price paid for the album, and the 3 predictor variables are participants' weekly disposable income, their estimates of what others would pay for the album, and the number of the band's albums that they already own. We're going to enter the predictor variables into the regression model on 2 steps or blocks. So on the first block, we'll enter disposable income and price that others would pay. And then on the second block, we'll enter the number of previous albums owned. And this will allow us to determine whether or not the number of previous albums owned can account for incremental variance in price paid beyond that already accounted for by disposable income and estimates of what others would pay. Now you can see in the data view that in total we have data from 65 participants. So in the Analyze menu, select Regression and then Linear. Move the criterion variable, which is price paid for the album, into the dependent field, and then move the block 1 predictors, weekly disposable income and price others would pay, into the independents list. Now click the Next button and move the block 2 predictor, which is the number of the band's albums already owned, into the independents list. In Statistics, select Confidence Intervals, R-square change, Descriptives, Part and partial correlations, and collinearity diagnostics, and then click Continue. In Plots, move Z-resid, which means standardized residuals, into the Y field, and Z-PRED, which stands for standardized predicted values, into the X field, and then select histogram and normal probability plot, and click Continue. And finally, in the Save dialog, select Standardized under Residuals and Mahalanobis and Cooks under Distances. Click Continue and then click OK, and your output will appear in the SPSS viewer.
In the data file, we have a variable set up for the description given to the teacher, their condition, and another for the grade that the teacher gave. If I swap to the data view, I can see that teacher 1 was told that the student was a bright student and they gave a B grade. I can see that teacher 2 was also told the student was a bright student and they gave a C grade, and so on. To analyse this data using a Kruskal-wallis ANOVA, we go to the Analyze menu, Non-parametric tests, Legacy dialogues, K independent samples. First, we want to move our test variable, the teacher's grade, into the test variable list. Next, we want to move our grouping variable, the descriptions given to the teacher, into the grouping variable list. Now next we want to click on the Define Range button here. This is where we enter the smallest and the largest values of the IV. For us, this was 1 for bright students and 3 for controls. We click Continue to close the box. And we want to make sure that Kruskal-wallis H is selected in the test type field. And then we click OK to run the ANOVA. You'll have the SPSS output pop up in the output window here.
In this video, we'll use a Mann-Whitney U-test to compare the median academic rank of the male participants with that of the females. We're using a Mann-Whitney test here rather than an independent samples t-test because our dependent variable, academic rank, is clearly ordinal, and it has 5 levels ranging from associate lecturer through to professor. So we have 2 variables in the data file. The first records each participant's gender as either 1 for male, or if we scroll down, 2 for female. And the second variable records each participant's academic level or rank using the value codes that we were just looking at. So in the Analyze menu, select Non-parametric tests and then Independent samples. Now under the Objective tab, select Customize Analyses and then move to the Fields tab. And in the Fields tab, move the dependent variable, which is academic level, into the Test Fields list, and move the independent variable gender into the Groups list. And then in Settings, underneath Choose Test, select Customize Tests, and select Mann-Whitney U. And now you can click on the Run button and your output will appear in the viewer. As we're working with two binary variables, all the participants in this study fit into one of just 4 categories. So there are participants who were in favour of stem cell research before watching the documentary and remained in favour afterwards. There are participants who were initially against stem cell research but changed their minds after the documentary. There are participants who were formerly in favour of stem cell research but are now against it. And then finally there are participants who were against stem cell research initially and they weren't influenced by the documentary. Now with a McNamara test of change we can determine whether or not a significant number of participants changed their views on stem cell research after watching the documentary. So in the Analyze menu, select Non-Parametric Tests, and then Legacy Dialogues, and then 2 related samples. Select the first of the 2 variables of interest, and then hold down the Shift key on your keyboard, and select the second, and then move the 2 of them across into the Test Pairs field. Deselect Wilcoxon as the test type, and select McNamara instead, and then click OK, and your output will appear in the SPSS viewer.
In the data file, we have 3 variables of interest: the age of the individual, their annual income, and their preferred political party. We can see that political party is a nominal variable and that it has 3 values: Greens, Liberals, and Labour. If I change the data view, I can see that the first individual was 30 years old, had an annual income of $108,000 a year, and preferred the Greens. To conduct the multinomial logistic regression, we go to Analyze, Regression, and Multinomial Logistic. First, we move the dependent variable, preferred political party, into the dependent field. Then we move all of our predictors, age and annual income, into the covariates field. Next, we open up the statistics menu. Now we want to make sure that pseudo R-square, step summary, model fitting information, classification table, estimates, and likelihood ratio tests are all selected. Click Continue to close the menu, and then OK to run the logistic regression.
In this video, we will use a one-sample t-test to compare the literacy test scores of a group of 28 students with the national average of 86.4 points. This national average was sourced from a government report. In the data file, there are 2 variables. The first is used to identify each student, whereas the second records their scores on the literacy test. The literacy test scores variable is a ratio variable, and consequently the measure type is set to scale in SPSS. Moving to the data view, if we sort the data file by right-clicking the column header and selecting Sort Ascending, we can see that student scores on the test range from 63 through to 88. In the Analyze menu, select Compare Means and then one sample t-test. Move the dependent variable, which is literacy test scores, into the Test Variables field and specify the national average test score of 86.4 in the Test Value field. This is the value that we want to compare the mean of the sample with. Click OK, and your output will appear in the SPSS Statistics viewer. Property values are generally positively skewed, and thus the median sale price for an area is usually more representative of the typical value of properties than the mean. So here we can see that there were many properties sold in capital city in the range of 300 to 500,000, but then there were a small number that were sold for much higher amounts than that. With a one-sample Wilcoxon test, we can compare the median capital city property price with the national average, which we already know to be $382,000. So in the Analyze menu, select Non-Parametric Tests, and then One Sample. In the Objective tab, select Customize Analysis, and then in the Fields tab, select Use Custom Field Assignments and move the variable of interest, which in this case is sale price, into the Test Fields list. Then in the Settings tab, select Customize Tests and select Compare Median to Hypothesized, and here you'll need to enter the value that you're comparing your sample median with, and in our case this is 382,000. At this point you can click the Run button and your output will appear in the viewer.
In the data file, we have a variable set up for the university course of the student with a value of 1 for medicine, 2 for dentistry, and 3 for podiatry. We have a variable for their stress scores at the start of the year and another for their stress scores at the end of the year. If I swap over to the data view, I can see that the first participant was studying medicine and had a stress score of 14 at the start of the year and a score of 29 at the end of the year. To perform the ANCOVA, we go to the Analyze menu, General Linear Model, and Univariate. Now we move our dependent variable, stress at the end of the year, into our dependent variable field. Next, we move our independent variable, university course, into the fixed factors field. Finally, we move the covariate, stress at the start of the year, into the covariates field. Next, we open up the model dialog and we make sure that full factorial is selected in the Specify Model field. Then we open up the Options dialog and we want to move our independent variable, university course, into the Display Means For field. Then we select Compare Main Effects, and in the Confidence Interval Adjustment drop-down, we select Bonferroni. In the Display field, we want to select Descriptive Statistics, Estimates of Effect Size, Observed Power, and Homogeneity Tests. Click Continue to close the dialog, and OK to run the ANOVA.
In a study of learned helplessness published in 1967, Seligman and Meyer reported an experiment in which 24 dogs were randomly assigned to 3 groups: escape, no escape, and control. Dogs in the escape and no escape groups were restrained and subjected to electric shocks. The dogs in the escape group could stop the shocks by pressing a panel with their heads, but the dogs in the no escape group had no control over the shocks. During this phase of the research, the control dogs did not receive any shocks. One day later, all 24 dogs were tested in a shuttle box. In a shuttle box, the floor that the dog is standing on becomes electrified 10 seconds after the light switch is on. To avoid a shock, the dog just needs to jump the barrier to the other side within 10 seconds. Each dog was given 10 trials in the shuttle box, and the data that Seligman and Meyer collected looked something like this. There are 2 columns. The first records which group each dog belongs to, and the second records their scores on the dependent variable. In this case, the dependent variable is the average time taken to jump the barrier by each dog, recorded in seconds. The grouping variable or independent variable has value labels, and these have been added in the variable view. So here we have used 1, 2, and 3 to represent the three groups of dogs. In the data view, each row is a dog. The first dog was in the escape group and had an average jumping time of 10 seconds. The ninth dog was in the no escape group and had an average jumping time of 60 seconds. To analyse this data, we'll use a one-way between groups ANOVA, which tests for statistically significant differences between three or more independent sample means. If the result of the ANOVA is statistically significant, we will follow it up with a set of post hoc tests. Each post hoc test will be used to make a pairwise comparison between two group means. So in the Analyze menu, select Compare Means and then One-Way ANOVA. Move the independent variable, which is group, into the factor field and the dependent variable time into the dependence list. Click Post Hoc. Here there are a range of post hoc testing options available. Because we don't yet know whether or not homogeneity of variances can be assumed, we'll select one option from each section, and later we'll make a decision about which to interpret. From the Equal Variances Assumed list, we'll select Tukey, which will test the difference between each pair of means. As we have three groups, SPSS will produce three Tukey tests, one for each pair of groups. We'll also select Games Howl, which we will interpret instead of the Tukey tests if we're unable to assume homogeneity of variances. Click Continue. In Options, select Descriptives, Homogeneity of Variance Test, and Welsh. We'll only interpret the Welsh test if homogeneity of variances cannot be assumed. Also select Means Plot, which will be useful for interpretation. Click Continue and click OK.
In the data file, we have variables set up for the children's ratings of the Allosaurus, the Space Shuttle, the Kite, and the Teddy Bear. If we swap to the data view, I can see that the first child rated the Allosaurus 7 out of 10, the Space Shuttle 2 out of 10, the Kite 7 out of 10, and the Teddy Bear 4 out of 10. To conduct the repeated measures ANOVA, we go to the Analyze menu, General Linear Model, Repeated Measures. First, we want to enter the name of our independent variable, toy, into the within subject factor name. Next, we want to enter the number of levels of the independent variable, or the number of toys, into the number of levels field. Click Add, and then click Define. Next, we want to move each level of the independent variable, each toy, into the within subject variables field. In the Options menu, move the grouping variable, toy, into the Display Means For field, and select Compare Main Effects. In the Confidence Interval Adjustment drop-down, select Bonferroni. Next, in the Display field, we select Descriptive Statistics and Estimates of Effect Size. Click Continue to close the menu and OK to run the repeated measures ANOVA.
In the SPSS variable view, three variables have been set up. The first records each participant's ID number, whilst the second and the third record their average reaction times to the 5 control trials, followed by the 5 experimental trials. If we switch to the data view, you can see that the participant with ID number 1 recorded an average reaction time of 345 milliseconds on the 5 control trials, followed by an average of 268 milliseconds on the experimental trials. And in total, you can see that there are 15 participants in this study. So in the Analyze menu, select Compare Means, and then Paired Samples t-test. Select both levels of the independent variable and move them into the Paired Variables field, and click OK. And your output will appear in the SPSS Statistics viewer. In this video, I'll show you how to run a principal components analysis in SPSS. As there are many menu options to select from, I'm not going to describe what each and every one does. Instead, I'm going to focus on providing you with the output that you'll need to be able to fully interpret and write up your results. In the companion video, which you can access from the StatHand website or mobile app, I'll walk you through the output that you'll get by following the instructions in this video. So let's get started. We have data here from 100 people who rated how important these 5 variables are to their decision making when choosing a place to go on holiday. So they rated each of these things on a scale from 1, which indicated very unimportant, to 5, which indicated very important. If I switch to the data view, you can see the responses that the first few participants gave to each item. And remember, the higher numbers, up to a maximum of 5, indicate a higher level of importance. So in the Analyze menu, select Dimension Reduction and then Factor. Move all of the variables that you want to subject to principal components analysis into the variables list. And if you click on the first item and then hold down the Shift key and then click on the last, you can select them all at once. So open up the descriptives dialog, and here initial solution should be selected by default. You should also select coefficients, significance levels, In this video, we'll use SPSS to run a standard multiple regression. Specifically, we'll use customers' disposable income and estimates of what others would pay to predict the amount that they chose to pay for a record which they were able to set their own price for. Now, price paid is the criterion or dependent variable, and weekly disposable income and price others would pay are the predictor or independent variables. And these are all ratio variables, and we're seeking to predict or account for variance in one, price paid, with knowledge of the others, disposable income and price others would pay. Now, as we have no rationale for entering the predictors into the regression model in blocks, we'll enter them simultaneously, and consequently we'll be running standard multiple regression. Now, if we move over to the data view and scroll down the screen, you can see that in total there is data here from 65 cases. So in the Analyze menu, select Regression and then Linear. Move the criterion variable, which is price paid, into the dependent field, and move the predictors, which are weekly disposable income and price others would pay, into the independents list. In the Statistics dialog, select Confidence Intervals, Descriptives, Part and Partial Correlations, and Collinearity Diagnostics, and then click Continue. In Plots, select Standardized Residuals and move it into the Y field, and then select Standardized Predicted Values and move it into the X field, and then also select Histogram and Normal Probability Plot, and then click Continue. In the Save dialog, select Mahalanobis and Cooks under Distances, and then under Residuals, select Standardized. And click Continue. And finally click OK, and your output will appear in the SPSS viewer. In this video, we will use a Wilcoxon-signed rank test to compare the sample's median ranking of the importance of GM ingredients to cereal purchasing decisions before the lecture with their median ranking of the importance of GM ingredients after the lecture. This is a repeated measures design, and thus we have two pieces of data from each participant. So for example, you can see that participant number 1 ranked GM ingredients second before the lecture, but first after the lecture. Participant 6 ranked them third before the lecture, but then fifth after the lecture, and so on. And because we're working with ranked data here, the measure type has been set to ordinal in the variable view. So in the Analyze menu, select Non-Parametric Tests and then Related Samples. Under the Objective tab, select Customize Analysis. In the Fields tab, move the two variables of interest into the Test Fields list. And these are the rankings for GM ingredients before and after the lecture. And then in the Settings section, under Choose Tests, select Customize Tests, and then Wilcoxon Matched Pair Signed Rank. Now you can click the Run button, and your output will appear in the viewer. When setting up the data file, you'll need two columns. The first column will record which group each case belongs to, and the second will record their scores on the dependent variable. Each row represents a case. The grouping variable or independent variable will require value labels, and these can be added in the variable view. So here we've used 1 to represent members of the male group and 2 to represent members of the female group. Back in the data view, we can see that the first participant is a male and has an IQ score of 100. The fourth participant is a female with an IQ score of 105. In the Analyze menu, select Compare Means and then Independent Samples t-test. Move the independent variable into the Grouping Variable field and click Define Groups. In the Define Groups dialog, enter the value labels used for the two levels of the independent variable. Move the dependent variable into the Test Variables list and then click OK. and your output will appear in the SPSS Statistics viewer.
In the data file, we have 4 variables of interest: the individual's level of satisfaction with their preferred political party, the individual's age, level of income, and preferred political party. We can see that level of satisfaction is an ordinal variable and that it has 4 levels, ranging from strongly dissatisfied to strongly satisfied. We can see that political party is a nominal variable and it has 3 categories: Greens, Liberal, and Labour. If I change to the data view, I can see that the first participant was strongly dissatisfied with their political party. They were 30 years old with an annual income of $108,000 per annum, and they preferred the Greens. To conduct the ordinal regression, we go to Analyze, Regression, Ordinal. First, we move our dependent variable, level of satisfaction, into the dependent field. Next, we move our continuous predictors, age and annual income, into the covariates field. And finally, we move our categorical predictor, preferred political party, into the factors field. Next, we open up the output menu. We want to make sure that goodness of fit statistics, summary statistics, parameter estimates, and tests of parallel lines are all selected. Click Continue to close the menu, and OK to run the logistic regression.
In this video, I'll show you how to run a type of exploratory factor analysis called principal axis factoring in SPSS. As there are many menu options to select from, I'm not going to describe what each one does. Instead, I'm going to focus on providing you with the output that you'll need to be able to fully interpret and write up your results. In the companion video, which you can access from the StatHand website or mobile app, I'll walk you through the output that you'll get by following the instructions in this video. So let's get started. We're going to factor analyze a 12-item measure called the humour scale. And I have data from 203 participants who responded to each of these items on a numeric scale ranging from 1 to 5, where 1 indicated strongly disagree and 5 indicated strongly agree. To make interpretation easier, I've included the actual wording of each of the items in the label field for each variable, and I'd recommend that you do the same. Now, if you read through these items, several of them appear to be about making fun of other people. So items like 1, 3, and 5. And several of them appear to be about making fun of oneself, such as items 2, 4, and 6. But then item 7 is slightly different. It seems to be about using sarcasm as a form of humour. We'll keep a special eye on this item as we proceed with the analyses and interpretation. So I'm just going to switch to the data view. And here you can see the responses that the first few participants gave to each item. And remember that higher numbers, up to a maximum of 5, indicate a higher level of agreement with a particular item. So in the Analyze menu, select Dimension Reduction and then Factor. Move all of the variables that you want to factor analyze into the variables list. And if you click on the first and then hold the Shift key and then click on the last, you can select them all at once. Open the descriptives dialog, and here you'll see that initial solution is selected by default. You can also select coefficients, significance levels, determinant, KMO and Bartlett's test of sphericity, reproduced, and anti-image. Click Continue. In the extraction dialog, there are a number of extraction methods available. In most circumstances, the differences between the solutions that they provide will be minimal. In this video, we're going to use principal axis factoring, as it's one of the more commonly used extraction methods for exploratory factor analysis. Also select Scree Plot under Display. Now we're going to extract factors based on the Kaiser criterion, which basically says extract factors with eigenvalues greater than 1. The alternative is to extract a specific number of factors, which you may want to experiment with if the default options don't provide you with an interpretable solution. Click Continue. In the rotation dialog, we again have a number of different options. Varimax, quartermax and equimax are referred to as orthogonal rotations, and they're used if it's assumed that the factors underlying the observed variables, which in this case are participants' responses to the scale items, are uncorrelated. Now the best way of finding out if this is the case is to use an oblique rotation, like direct Obleman or Promax. And in this case we'll use direct Obleman. An oblique rotation allows the factors to correlate as necessary, and thus it often provides a more realistic solution. Finally, in the Options dialog, select Sorted by Size and Suppress Small Coefficients, and change the absolute value below to 0.3. The reason that we're doing this is to make interpretation of the final output easier. Click Continue, and then click OK, and your output will appear in the SPSS Statistics viewer.